Okie dokie, everybody. We're going to start talking about potential energy today. Check out this cool intro. All right, interesting enough. All right, so here's a bunch of notes. Gravitational potential energy. It is stored energy. I mean, we're going to have different types of potential energy. Specifically, right now, we're talking about energy stored in a gravitational field. Is it due to its position? Well, that was almost English, but this is a one-take deal, so, well, you know. Potential energy stored due to its position. Okay, and then we have some things in here like if no energy is lost to friction, like what are we talking about here? Then the work done in moving it to that position is equal to its potential energy. Right? So you are giving it energy by doing work on it. If you are putting it in a particular place, it is gaining energy because of that work that you did. Okay, so here's the generalized formula for it. It's gravitational potential energy is equal to mgh. That's mass times gravity. In other words, mass times gravity, that's the weight, so that's like Fg, okay, times however high it is. Now, you'll see in your reference table that it says delta H there. That's no big deal. We are going to be clever, and we are always going to choose our lowest point that the problem is going to let us go to as a 0. So we are just going to ignore that delta and just think of this as mgh. It's the only way I'll ever write it. It's a good way to think about it. Okay, next. Whoop, back out here. Okay, here's an example, right? Stick figure guy lifting a blue box again. Cool. What's its energy when it's on the ground? Well, it does have weight because it's a 10 kilogram box, right? It actually has mass, so therefore it has weight. So that mg, that's a value. It's a 10 kilograms times the g, 9.8. So what is the work that's done on it? Nothing. It's just sitting there. So what is its gravitational potential energy? Nothing. It's just sitting there. 0 potential energy at that point. It's on the ground. It's at its lowest point. Well, what if you say, Mr. Ross, I have a question for you, and my question is what if I were to lift that block up 1 meter, and it were to suddenly go from 2-dimensional to 3-dimensional, but like a not well-drawn 3-dimensional, then what would its energy be? Well, then it now has a height of 1 meter. So you have its mass, 10 kilograms, boom. You have its gravitational acceleration, that's the g, 9.8 meters per second squared, boom. And then you have its height, which is now 1 meter in the air. So you have applied the force, i.e. its weight, okay, Fg, times the distance up in the air that you've raised it. That's F times d. Okay, so that is the 98 newtons times the height that it goes of 1 meter. So that's 98 joules of work that you did on it. And guess what? It also gains 98 joules of gravitational potential energy. But then you say, Mr. Ross, that's all well and good. But what if I were to raise it another? That's right, another 1 meter. What would it be then? Well, you say it's 2 meters high. I say we'll have twice as much energy then. Right? If we double that height, we are doubling the gravitational potential energy that it has. Boom. All right, we do another 98 joules of work, which means it gains another 98 joules of gravitational potential energy. So the total gravitational potential energy is, as you lift that block, which is now 2-dimensional again, you might have noticed, and also quite a bit larger, unless we're looking at it from another orientation. Maybe it was some sort of parapiped or rectangular prism as opposed to some kind of cube, which it looks like in that first diagram. Well, whatever. All right, so we now have 196 joules of gravitational potential energy. Okay, so pretty much the deal is if you raise something higher, it has more energy stored. If it has a bigger mass, it has more energy stored as it's raised up into the air. So the bigger the mass and the larger the height, the more energy it has stored in that gravitational field. Pretty straightforward, if I do say so myself. So you can think about it as when we are lifting something, the minimum force you need and the force that we then apply is the weight of the object, Fg, which we can also write as mg, which is the equation that we ultimately use. What if you don't lift it straight up into the air? What if you are a stick figure that has no neck and is pushing a giant red ball up a very long ramp, 50 meters long? That's a weirdly specific question that you bring up, but I just so happen to have a diagram that meets that need. Okay, so you are going to push it up this incline. If it takes you 5 newtons of force to get it to go up the incline, how much work do you do? Well, you have your 5 Newton floors. One take, I'm going to have to roll with it on YouTube forever. Okay, so you have that 5 Newton force, 50-meter distance, 250 joules is the work that you get when you multiply those things together. But how much gravitational potential energy does it gain? Well, it gains that same amount. And you are so excited by that fact that you leap off the ramp for some reason. But luckily, you're a stick figure in this weird example. It gains 250 joules of gravitational potential energy. This is specifically in the case where, what is happening there? When no energy is, quote unquote, lost, right, used up as a result of some interaction between friction. So this is a frictionless example. If there was friction, then we'd have to do some different things here. Okay, so gravitational potential energy gained is equal to the work done in putting it into that place in the system when there is no friction. All right, so the more work you have to do to raise it up, the more gravitational potential energy it has. Okay, mgh. All right. So let's take a look at a different example. Let's actually tell you something about the ramp, like an angle, okay? And then you can figure out the height. All right, so we have this 15-kilogram blue crate, and we are going to raise it 75 meters. But we're not, at least at first, going to lift it straight up. We are going to push it along the ramp. You might say, isn't that easier? Wouldn't I be doing less work? Then how does it have different amounts of energy? Or does it have the same amount of energy? Good question. So you're pushing this up at some constant speed, and you are pushing it up with just the right amount of force, right? Just so it starts to go up the ramp. And you figure it out. You do your math, and you say, well, the force that I have to push it up to make it go up at a constant velocity is the same as the component of gravity that's pulling it down the ramp, right? So we talked about this before in terms of the FGX, right? The part of gravity that is parallel to that plane is the force that you would need to counter up the plane in order for it to move at a constant speed. Okay, so if Fg is equal to 147 newtons, right? Fg is equal to mg. To push it up the incline, you would need to apply a force, and that's that Fg sine theta business there. I'm skipping over some of this stuff because our focus here is really on the energies and how we know some of these things. So Fg sine theta, that portion is 73.5 newtons. That means gravity is pulling it down the ramp with 73.5 newtons. The total force gravity is applying is 147 newtons, but the part that's actually pulling it down the ramp is 73.5 newtons, which means if you want to push it up the ramp, which you do for some reason, I don't know, that you need to push up with 73.5 newtons to overcome that downward force. If that long ramp, 150 meters, okay, longer than a football field, if this is drawn to scale, this is a giant person and a giant box, all right? And 75 meters is pretty tall as well. Who picked these numbers? I have no idea. So, by the time you get to the end of 150 meters, you have done 11,025 joules worth of work on the box. Okay? So how much gravitational potential energy does that have in this non-friction world? Well, according to that previous slide, you would say, Mr. Ross, doesn't it have to have the same? How is it possibly going to have the same? Well, don't you worry, I'll show you. All right, so it's that you take that same, I'll just stutter all day and then put it on the, put it on the internet. All right, so you take that same weight, that 147 newtons, and instead you multiply it by the height. If you don't believe me that 75 meters works as a triangle here, you can do the math yourself, but it does. So you multiply that 147 by how much you displace it vertically, and yes, indeedly doodly, little Ned Flanders reference, you do get the 11,025 joules. You would get the same answer if you used the mass, 15, times the acceleration due to gravity, 9.8, times the height of 75, right? M times G, that's 147, times 75, 1125. 11,025 joules. Okay? Pretty dang exciting. All right, so hope this makes sense. Just a quick hitter in terms of gravitational potential energy. We'll talk to you later. Have a great day. See you tomorrow. Just kidding. Goodbye.